bubbly, 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 burn, burn, burn. It's chemistry! Woohoo! Let's do some chemistry. Yeah! Hey, good morning. Here we are again. What are we going to talk about today? We're going to talk a little bit more about Chapter 17 and these reactions as well as reaction rates and stuff. We're going to look at a tiny little, I guess, conceptual sketch, a reaction pathway. You should be able to complete the sketch yourself and give values, and it's in a little chart. It shouldn't be too bad. But by the by, we've kind of changed homework structure. You guys are only going to be doing kind of quizzes on Fridays until the whole thing's done, and all the assignments should be in Plan Book for you to look at, Plan Book and Power School. So let's get through this one. This is what I'm going to call 17.1b, second kind of section talking about reaction pathways. All right, got our handy dandy whiteboard out. We're ready to kind of go here. Let's look at reaction pathways. So some of the words you're going to need to know for this. We're going to need to know the words reactants, products, activation energy, and it's written like that. So this is activation energy. And we'll probably have to look at delta E, which is the change in energy as you move from reactants to products. So there's some vocab in there. You're going to have to kind of go take a look at that vocab, make sure we understand those. Those should be pretty straightforward, pretty easy. So let's look at what we call a reaction pathway. Let's just say we have some reactants, A plus B, reacting to form A B. Well, we've already talked about a couple of things. We know that these two have to collide in the right orientation with enough energy for this to actually occur. So let's just kind of look at a little simple reaction pathway here. And so what is it going to look like? It's going to look like this. We're going to have energy increasing, and down here we have time or course of the reaction. And so we could do something like this. We could say A and B. Maybe they start at relatively low energy, right? And then maybe their reaction pathway takes them up this hill and then down to here where we have A, B. Well, now we have some things here. We could look at a delta E. We could look at delta E. If I gave this a value of 50 and I gave this a value of 100, we can mathematically kind of deduce our delta E. So again, these are in kilojoules. Don't forget, these are in kilojoules per mole. And so 50 kilojoules, 100 kilojoules, we know our overall change in energy should be about 50 kilojoules per mole. And that was a positive value. It looks like it's pulling energy in. Low energy, high energy. So that's going to be an endothermic reaction. It's going to feel kind of cold if we look at that delta E, that we have stored more energy in there. So we have this weird little hump here. This little hump is our activation energy. It is the energy required to get that reaction to occur. A lot of times at this point, at this very top of that hill, remember when we were talking about mechanisms and we talked about intermediates? That's where our intermediate exists. Maybe what really happens is maybe there's two A's that run into two B's and they form this weird complex like this, some crazy complex that exists transitionally for a microsecond before it decomposes back into AB. Just an intermediate, we call them an activated complex. They kind of lie at the top of activation energy. And so that's your basic kind of graph. Don't forget, we need to know that. Activated complex or intermediate. I think we're okay with that. Now, again, we've been looking at a mechanistic approach. We know that things happen in multiple steps. And so if we wanted to, we could look at maybe some reactants starting here, and they go through an initial little hump to here, and then we go through another hump to here, and maybe another hump all the way down to here. Well, we could look at the sum of all of the delta E's. We could take delta E1 plus delta E2 plus delta E3 and come up with a complete delta E. I think you understand what I'm saying there. And again, these are all different activation energies, and that means there would be a different intermediate or activated complex at each one of these little humps. If we look, though, our energy here and our energy at the end, well, our final energy is much lower than our initial energy, so this is an exothermic reaction. Again, this is a mechanism that would have taken place of 1, 2, 3 steps, and then again, it's just math. It's adding positives and negatives. So I think you should be okay with that. Practice that. Make sure you understand what I've talked about when it comes to those kind of things. Last word we really got to talk about is this one: a catalyst. Catalyst. It's how you keep your bovine in check. Well, you have a list. Mine always looks like scroll, right? And maybe there's a heifer, maybe there's a cow, maybe there's a calf and a bull and an Angus. That's my cattle list. No, I'm sorry. That's all right. Starting over. Catalyst. Chemical catalyst. A catalyst. Ready? What does a catalyst do? Here's my reactants. Here's that bump. They're going to products. This is my activation energy. Well, a catalyst lowers activation energy. It makes that hill smaller. So a catalyzed reaction, its hill would start off the same, and then all of a sudden, boom, catalyzed. It lowers the activation energy. That's the purpose of a catalyst. I can do that in a couple different ways. Increase number of collisions, create orientation that's proper. All of those kind of things reduce activation energy. Well, folks,